Okay, we'll pick up with section 11.4. We're talking about the comparison tests. Again, these are two tests. So one is the comparison test, okay, just a regular comparison test, and then we'll look at the limit comparison test also in this section. So yeah, let's just look at one more example of using the comparison test. Suppose that we have the summation as n equals 1 to infinity of 1 divided by 2 plus the square root of n. Okay, so I mentioned in the last video, you know, it's very natural to compare the sequences with other sequences where you're like disregarding terms here. So like if I just disregard the 2, 1 divided by 2 plus the square root of n, and I'm comparing that to 1 over the square root of n. Okay, well, the left side is always going to be less than the right side because the left side is always going to have a denominator that's going to be a bigger number. So the entire number on the left side is going to be a smaller number than compared to the one on the right. Okay, this comparison would be useless though, because the summation as n equals 1 to infinity of 1 over the square root of n diverges. Right, so this does not tell us whether the original series converges or diverges. Right, I could still have a convergent series. You know, if I'm adding up a bunch of terms and they're all less than the one for 1 over the square root of n, when you're adding those up, you know, how do you know that that series converges? You know, it might. So sometimes, you know, when you're looking for the comparison, be aware of that. Okay. This comparison doesn't help us at all. Okay, so now with some experimenting, it can be seen that 1 over n is less than or equal to 1 over 2 plus the square root of n. Now this statement doesn't happen until n is greater than or equal to 4. Okay, now all we need to do is show that the comparison happens for some value n, you know, in this problem, and I'll comment on this after we've looked at where this n greater than or equal to 4 comes from. So I'm looking at this statement here: 1 over n less than or equal to 1 over 2 plus the square root of n. Okay, and if I cross multiply on that, I got 2 plus the square root of n less than or equal to n. Okay, get all the terms onto the right side. And n minus the square root of n minus 2 is greater than or equal to 0. Okay, I'm going to use a u substitution on this. Okay, if u is the square root of n, then if I square both sides, u squared would be n. Okay, I've got an n leading off, so I'll replace it with u squared. Minus the square root of n is what I'm calling u. Okay, and then minus 2. And I'm going to just temporarily set that equal to 0, as if I had a quadratic equation. Okay, this quadratic will factor as u minus 2 times u plus 1, and when I set each of those equal to 0, u is equal to 2 or u equals negative 1. Okay, now I don't care what u is. U is just a temporary variable to help me solve this for n, right? Where this inequality here is involving n. So let me go ahead and substitute back. U is the square root of n, so the square root of n equals 2, or the square root of n equals negative 1. The square root of a number can never be a negative, right? So I can go ahead and cross that one off. I don't need to bother solving that one anymore. The square root of n equal 2 means that n is equal to 4. Okay, that's where the 4 comes from. So if I have 4 on the number line there, any number that's greater than 4, so like if I let n be 9, we'll say, this statement should be true here. So 9 is greater than square root of 9 is 3, plus 2 is 5. 5 is less than or equal to 9. That's true. Okay. Any number that's greater than or equal to 4 means that this statement is going to be true. And so this statement here, 1 over n is less than or equal to 1 over 2 plus the square root of n, that's also going to be true, not until n is greater than or equal to 4, though. Okay, so now my original series was where I'm starting at 1. Okay, so I'm comparing this to 1 over n, which I know is a divergent series. Now, and I'm comparing term by term, with something that's divergent, and I'm comparing the sequences here with where the right side is always bigger than the left side. Okay, so I'm going to have also a divergent series. Now, the fact that I'm going to add 1/2 plus 1 over so 1 plus 1/2 plus 1/3, to this, that doesn't matter, right? Because this statement would be true for when n is greater than or equal to 4. Okay, the summation as n equals 1 to infinity of 1 over n diverges. Therefore, the summation as n equals 1 to infinity of 1 over 2 plus the square root of n also is going to diverge. Okay. Now, the point of this is to say that, when you're finding your comparison sequence, I mentioned typically you're going to be, comparing this to a geometric series or a P series, okay? And don't necessarily give up, if you get something like this that's not true, okay? Okay, let me talk about the limit comparison test next. We'll look at this same example here as the first one. That says let a sub n and b sub n be sequences that are positive. If the limit as n approaches infinity of a sub n divided by b sub n is equal to L, and L is some positive number, then the series given by the sum as n equals 1 to infinity of a sub n and the sum as n equals 1 to infinity of b sub n either both converge or they both diverge. Okay, so let's see. Now up here, I was comparing this to 1 over the square root of n. That just a standard comparison didn't help me. Okay, now what if I were to use the limit comparison test? Okay, so a sub n is always going to be your original sequence here that's in the sum. So that's going to be 1 over 2 plus the square root of n. And b sub n, so what if I didn't have the plus 2? What if I let b sub n be 1 divided by the square root of n? Then the limit as n approaches infinity of a sub n over b sub n is the limit as n approaches infinity of 1 over 2 plus the square root of n divided by 1 over the square root of n. And when I flip the denominator there, I got the limit as n approaches infinity of the square root of n divided by 2 plus the square root of n. And if I multiply the top and bottom of this fraction here by 1 divided by the square root of n divided by 1 divided by the square root of n, that's the same as 1, I'm not changing anything, right? Then with that, I get square root of n times 1 divided by the square root of n, that's 1. And then 1 divided by the square root of n times 2, that's 2 divided by the square root of n, plus square root of n divided by the square root of n, that's 1. Okay? And the limit of a constant is always the constant. The limit as n approaches infinity of 2 divided by the square root of n. The denominator is going to grow without a bound as the numerator just sits at 2. So the corresponding y values are getting closer and closer to 0. So this limit would be 1. Okay? Now, according to the limit comparison test, both of the series converge or they both diverge. Okay, I'm comparing this to a p series where the p-value is 1/2. I know that this is a divergent series. Okay, therefore, because the sum as n equals 1 to infinity of 1 over the square root of n diverges, then that means that the original series is also going to diverge. Okay? There's a note there next. It says, suppose that the two sequences are positive with the sum as n equals 1 to infinity of b sub n divergent. Okay, then the limit as n approaches infinity of a sub n over b sub n equals infinity. That also means that the the sum as n equals 1 to infinity of a sub n is also going to be divergent. So it's not necessarily that you're going to have some positive number. You could have infinity also. Okay. So let's check it out here. I was using 1 over n, and if you're wondering where that's coming from, okay, I was using some creativity, and again I'm selecting a series that's either a p series or a geometric series. A geometric series isn't going to work here, but what if we stick with 1 over n, okay? And 1 over n isn't going to be, a natural first choice. It's, 1 over the square root of n would be naturally what you check for with b sub n. We get the divergent series there. But suppose that a sub n is 1 over 2 plus the square root of n, and b sub n is 1 over n. Okay, then using the limit comparison test, I get the limit as n approaches infinity of a sub n divided by b sub n. That is equal to the limit as n approaches infinity of 1 over 2 plus the square root of n divided by 1 over n. And when I flip the denominator there, I'll have the limit as n approaches infinity of n divided by 2 plus the square root of n. Okay, you can use L'Hopital's rule if you want, or if you multiply the top and bottom by 1 divided by the square root of n. N divided by the square root of n, that's the square root of n. And then I'm dividing that by 2 divided by the square root of n plus 1. N is approaching infinity. So n is approaching infinity means that 2 divided by the square root of n, that's going to be getting closer and closer to 0. And I'm adding 1, so I'm not dividing by 0, right? And the square root of n, as n approaches infinity, that'd be infinity. So I'm looking at infinity divided by 1. That's infinity. Okay. Well, I was comparing this to a divergent series. The sum as n equals 1 to infinity of 1 over n diverges. And so that's going to mean that the original series here, the sum as n equals 1 to infinity of 1 over 2 plus the square root of n also diverges. We have the limit comparison test there. Okay. So now the limit comparison test is a very important test. Okay, just like the regular comparison test is an important test. Okay, be sure that you know both. Okay, you will see both all over the place here. We'll look at I got 2 more examples in the notes there, and we'll hit that in the next video there. Okay.